Before we start, I just want to go through quickly the stuff that I did at the beginning of last lecture, okay, about the acid leak and the fumes and whatnot, which is why Fred is here. So some of you might have noticed when I was going through the calculation that I made a mistake. There was a power of 10 in the calculated concentration of acid vapors in the atmosphere, so I actually used a value of 10 ppm of HF in the atmosphere, and it was actually more like 100. So I just thought I'd show you, this is Fred at the front here. So I didn't actually kill Fred by taking him back into the lab too quickly. So just going through the calculation with the correct number. So at the top, we've got the lab, okay, and let's imagine that lab is full of acid fumes to the concentration of 10 parts per million of HF. And we've got air coming into the lab and air going out of the lab. Okay, so every time we replace one volume worth of air, okay, we're not basically pushing out some air and replacing it with completely fresh air. It mixes. So it's like, imagine you basically doubled the volume of the lab and then mixed up the concentration and then reduced the volume again. So every time you fill up the lab with air, you're effectively halving the volume of the contaminant. Okay, so that's this kind of statement here. So in 1 hour of flushing air through the lab, 100 ppm will go to 50 ppm. Okay, so that's just reflected in this equation here. Okay, so 100 is equal to basically a halving once. Okay, so if you do it for 2 hours, you'll be timesing it by a half twice. 3 hours, a half 3 times. Okay, so the question is, how long do we have to wait? Okay, so what do we have to make this power to make 100 into 0.5? Okay, and just simply to do this, you rearrange the equation to get the fraction that you want to change over on the left-hand side. Then you take the logs of both sides. Now, it doesn't matter which base log you take, as long as you do the same to both sides. So that's what's going on here, allowing us to work out actually that to go from 100 to 0.5 ppm, we only need just under 8 hours. Okay, and we did wait 8 hours, right? We waited 16 hours. So I still also made Fred wear this ridiculous kind of like respirator thingy to go in as well. And it was kind of safe. Okay, so we're going to start today's lecture now, which is about the ocean carbon cycle. So yesterday we went over the land carbon cycle, looking at fluxes between the biosphere and the atmosphere and how those change seasonally. Okay, so we'll be essentially doing the same thing for the ocean, looking at what are the fluxes, and then looking at some of the chemistry of carbon dioxide in water, and that's what this kind of like experimental thing at the front is going to be demonstrating, which Fred will kind of help out on. Okay, so this is the kind of the bit that we did yesterday, this accounting for this extra flux into the atmosphere, and then kind of figuring out that actually the rise in concentration in the atmosphere is less than we would expect, and all of we basically explain away some of that by increasing efficiency of the biosphere. But today we're also going to be talking about this ocean sink. So some of this carbon dioxide that we're putting into the atmosphere from fossil fuels is actually going into the ocean. Okay, because the flux in and the flux out are not in balance. Okay, so this is a simplified kind of zoom in on the kind of reservoirs within the ocean. So we've got the exchange with the atmosphere. So that only exchanges with the surface ocean. Okay, and then once the carbon gets into the surface ocean, it gets taken up by the biosphere. So things like phytoplankton, those get eaten by kind of larger zooplankton, which get eaten by fish, which get eaten by other fish, which then get eaten by us. And that allows there to be, well, that sinking kind of dead organic matter is a flux into the deep ocean. We'll look at that, but there's also a flux of mixing between the two. Okay, so we'll look at the proportionings of carbon that's basically locked away in these pools that can't interact with the atmosphere. Okay, and we'll see that that's both kind of like a physical separation by moving stuff into the deep ocean, but also there's a series of chemical reactions which prevent carbon exchanging back up with the atmosphere. Okay, so the kinds of forms of carbon we're going to be looking at, we're going to be using dissolved inorganic carbon, and we'll see in a bit that that's not just this HCO3, which is called bicarbonate. And then there are forms of organic carbon as well. Okay, so the thing we're going to start out with is this concept of Henry's law. So this is basically if you've got some amount of carbon in the carbon dioxide in the in the air above water, some of it will go into the water and dissolve. Okay, so we're just going to go do a quick demonstration of that, which I will try and video for the people who are, let's say, revising at home. So what we're going to do here is, so this is tap water. This is not Perthshire bottled at source. This is bottled in the toilets. And all I'm doing is putting it in this bottle for soda streaming. Okay, and I'll just put a bit in the little doobie what's it there. And put that down somewhere safe so I don't pour it over the projector. So all I'm going to do now is I'm going to add CO2 to this. Okay, so I'm basically going to fill this headspace here with carbon dioxide, okay, to a high concentration, okay. So that's going to cause the CO2 to dissolve in the water, okay, and ultimately the concentrations of those in the headspace in the water will start to approximate this solubility constant, okay. It determines how much CO2 will dissolve in the water. So I'm going to carefully put this in here. Okay, so that's, I assure you that's safe. Yeah, okay, and you might be able to see that that's kind of fizzy now. So what I'm going to do is pour some of this into this scientific beaker, pesto jar. So what I have now is I've got some water from the tap that's got no CO2 in it, or very little CO2, and I've got one that's been in kind of equilibrium with a very high concentration, okay, or high partial pressure in the headspace above it. So this is methyl orange. You might have come across this in school. It's a pH indicator. So if I put a bit of that in there, you can see that it's kind of orange. Put some more just for shits and giggles. Okay, and if I put some in the one that we've added CO2 to now, okay, here we go. I'll pop that down there so I don't knock it over because that's, semi-hazardous. Okay, so you can clearly see now that one is a little bit more orangerer than the other. Okay, so this one has gone redder, so this means that it's been acidified. And we'll see in a bit that actually when carbon dioxide reacts with water, it actually forms an acid. Okay. So we can use the acidity, in this case, as some proxy of the carbon dioxide concentration. Okay? So what we're going to do now is we're going to suck up a little bit of this, this water. Yeah. You and my glamorous assistant can hold that. And he is very glamorous. Oh, I wanted to put it in the other one, didn't I? Actually, can you squirt that one out? I need to fill it with this one. Sorry, my bad. Yeah, fill it with that one. Okay, so what I'm going to do now is we've got our basically carbon dioxide rich solution here and another carbon dioxide rich solution there. And what we're going to do is, so I'll put a bung over the end. I'm just going to, you can hold the spiky thing. I'm just going to basically suck the piston out to lower the pressure of the gas inside here. Where's the hole? There we go. Okay, so you might be able to see that it's kind of, the gas is now bubbling out of solution, okay, because now the ratio of gas or the ratio of the partial pressure in the headspace to the dissolved liquid wants to re-equilibrate to this solubility constant, okay. And we can kind of see this happening now if we kind of give this a bit of a shake, let it degas a little bit more. So you can now see that, I'll hold that once it doesn't drip everywhere, that this one is a little bit more red than this one. Okay, because the CO2 has now gone out of the water, it's unacidified. Okay, we can take it round so people can actually maybe be convinced. This one is a little bit redder than this one. Maybe. It's not that impressive. Yeah, okay. Okay, so we can see now that basically there's this relationship between the pressure of the gas, or the partial pressure, which is essentially the pressure times the concentration in the headspace, and the dissolved gas in the solution. Okay, so this is quite important. So if we increase the atmospheric concentration or partial pressure of CO2, the ocean concentration will correspondingly go up. Okay, so that's kind of leveled kind of semi-safely down there. Big, sharp, spiky thing. All right. Let's pour some of that on the floor. Yeah. Okay. Well, thanks, Fred. So big hand for Fred. Everyone, yay, Fred. Still alive, which is quite nice. I'll put the camera back on for the people that are revising at home. Right. So back onto this lecture. So this is this thing we went through the other day. And this solubility constant is temperature dependent. So the colder the water is, the more CO2 will dissolve in the water than will be in the atmosphere above it. Okay, so this is kind of explaining all of that kind of shit there. So we see in these cold regions, that allows there to be a flux of carbon into the ocean, and the warm regions, there's a flux of carbon out of the ocean because of this solubility constant is temperature dependent. It comes out like that. Okay, so this is kind of explaining some of these fluxes between the atmosphere and the ocean. So that solubility of gas in liquid is responsible for those fluxes there, okay, into and out of the ocean. But we've just seen that it's not just gas dissolving in liquid. There's a series of reactions that happen. So when carbon dioxide, over here, when that reacts with that doesn't just dissolve in water. It actually reacts together, okay, with water molecules to form this species here, H2CO3, which is called carbonic acid, hence the acidity of the solutions. And that is acidic because this molecule breaks apart really rapidly. It's very, very unstable, and it tends to break apart into this bicarbonate ion, and then it breaks apart further into this carbonate ion. And you can see that those two kind of subsequent reactions release a hydrogen ion, and that is what creates the acidity in the water. Okay, so this is basically once stuff comes out of the atmosphere, it goes into the ocean, and once it's in the surface ocean, these reactions happen almost instantaneously. Okay, and this means that actually most of the carbon that dissolves in the ocean is no longer the carbon dioxide molecule. Okay, it's these other forms of carbon, these carbonic acid, bicarbonate and carbonate. Okay, and you can see that actually from this just stock of them, most of the carbon is this bicarbonate species. Okay, so this is really important. I guess these are those reactions written out separately rather than all in one go. Okay, this is really important because only the carbon dioxide molecule can exchange with the atmosphere. Okay, all of these other forms of carbon, okay, they're not gaseous. Okay, so they can't get back out of the ocean. Okay, so what this means is that the Henry's law determining of how much carbon can be in the ocean is kind of determines the concentration of the CO2, okay? But there can be much more carbon dissolved in the ocean because these species here basically don't count towards the exchange with the atmosphere. So this is one of the reasons why the carbon has got much more, this is the reason why the ocean has got much more carbon than the atmosphere. Okay, so this is those percentages of the different species, and because when CO2 kind of reacts together with water to form carbonic acid, which then goes to form carbonate ion, because every time one of those reactions happens, it releases a hydrogen ion. Okay, so that makes those reactions, the equilibrium points of those reactions, dependent on the pH of the solution. So at high pH, okay, you've got lots and lots of carbon, you've got lots of hydrogen ions kind of floating around in the water. So that wants to force the reactions, okay, more towards the left-hand side, more towards the reactants, okay. So that means that CO2 is favoured, okay. Whereas at very, very low pH, okay, that basically removes the hydrogen ions from the water, okay, and the reactions want to basically move to the right-hand side. Okay, so if we just flick back to these, it wants to move back to the right-hand side of these to add hydrogen ions back in to basically kind of account for the high pH. Okay, so at high pH we have mostly carbonate. At low pH we have mostly CO2. And if you can see, the pH of the ocean is around here, around 8.1. You can see that only a very, very small proportion of the dissolved inorganic carbon is actually CO2. So that's the only bit that can exchange with the atmosphere, and the other species, bicarbonate and carbonate ion, they're basically locked away in the ocean and they can't exchange with the atmosphere. Okay? So that means that the concentration of CO2, which is basically this amount, is determined by the exchange with the atmosphere. Okay? And then the amount of carbon that is stored in the ocean is basically dependent on the pH. So that determines basically the size of these reservoirs compared to this one. So this is it kind of explained in the kind of the box kind of reservoir approach, that actually the carbon dissolved in the ocean, and I guess this box could also be kind of down for to explain the deep ocean one as well. It doesn't just go into the surface ocean, it then splits apart into these kind of three different phases. Okay, so it splits apart into CO2, aqueous, and then carbonate ion. I don't know why this at 4 degrees C is still here, just ignore that. And the carbonate ion, and you can see that these terms here don't interact with the atmosphere. Okay, which means that basically the Henry's law, the dissolution of CO2 in water, that's just the ratio of basically this amount to the size of this box. Okay, whereas the amount of carbon stored in the ocean is a ratio of this box to these boxes. And actually, if you plot it up in terms of the total amount of carbon stored in the ocean rather than just the relative proportions, okay, so the graph before was basically the total carbon, well, the amount of each species, CO2, bicarbonate and carbonate, divided by the total amount in the ocean. If you instead just look across a range of different pHs, what's the total amount of each carbon species in the ocean? So at low pH, you have almost all of the carbon is at CO2 form, but you can't store much total carbon in the ocean, okay, because you don't have any of this kind of these other pools which can't interact with the atmosphere. Okay, so this amount here is basically just determined by how much is in the atmosphere and how big the ocean is. Okay, but as the pH rises, you can start to lock away more carbon in these forms, the bicarbonate and the carbonate, which can't interact with the atmosphere. So the higher the pH gets, the more carbon you can put in the ocean. Okay, and you can see that this is a logarithmic scale over here. So this is a really dramatic increase in the amount of carbon you can put in the ocean by changing the pH a little bit. Okay, so this is a real problem for us, because if we add carbon dioxide to the atmosphere, okay, we've just seen that actually acidifies the ocean. Okay, so not only are we putting more carbon dioxide into the atmosphere, some of that is going into the ocean, but we change, by adding that CO2 into the ocean, we're changing its pH. Okay, so the pH will be slowly coming down. Okay, and that means that the more carbon dioxide we put in the system, the less the ocean can actually hold. Okay, which means proportionally more will ultimately end up going to the atmosphere. So by adding CO2 to the atmosphere, we're acidifying the oceans, we're actually reducing the capacity of the ocean to store carbon out of the atmosphere. Okay. Yeah, so I guess some of you might be thinking about why I've got this atmosphere is fixed at 280 parts per million, because you have to do these calculations, you have to tell it how much carbon is in the system. Okay, so if you say that there's more in the atmosphere, that means there will be more in the ocean at low pH due to Henry's law, and then there will be more everywhere. Okay, so just to do some kind of basically rough and ready calculations, just to see if we understand what's going on. Say at 4 degrees Celsius, the solubility constant is 3 grams per kilogram per atmosphere. Okay, so if we had 1 atmosphere pressure of CO2, so if the atmosphere was 100% carbon dioxide, okay, we could put 3 grams of carbon dioxide in water at 4 degrees Celsius per kilo of water. So we don't have 1 atmosphere of CO2. The pressure is 1 atmosphere, but the concentration is 400 parts per million. So our partial pressure is 400 microatmospheres. So we can then effectively work out the concentration of CO2 in water, which is the solubility constant times the partial pressure, which gives us this 1.2 milligrams of carbon dioxide per kilo. We can convert that into kind of sensible units rather than milligrams of CO2. We can put it into millimoles. to keep it in, SI units, we all like those. And if we know the concentration and the mass of the ocean, okay, we're assuming that all of the ocean is 4 degrees C and it's all equilibrated with the atmosphere, but these are kind of like, rough and ready calculations. We can then times the concentration by the mass of the ocean to work out how many moles of carbon dioxide there are. Then we can also work out the mass of carbon. Okay, so quite often you might see in the literature and in kind of publications in the popular media, people converting or misconverting between amount of CO2 and amount of carbon. Okay, so the number of moles of those two things are the same, but if you're thinking of mass, the mass of CO2 is 44 per mole, whereas the mass of carbon is only 12 per mole. So you quite often get a couple of publications that have that conversion done wrong, which is a shame. But we can basically work out what basically the CO2 in the ocean is. We can get this value here, about 450 gigatons of carbon. But that's only the carbon that's in CO2 form. Okay, so we know only 1% is in CO2, 99% is those other forms of carbon. So to work out the total amount of carbon in the ocean, we divide by kind of basically 1% to get this kind of 450 gigatons of carbon. Okay, so we've just gone through those calculations to see if we understand the processes, and we can check our answer. So the actual value is actually 3,800 gigatons of carbon. So we're quite close, but there are some things in our assumptions which are not quite right. Okay. One of those is, do we forward a bit? Oh no, anyway, so one of those assumptions might be that maybe not all of the ocean is at 4 degrees C. If some parts of the ocean are warmer, then we would expect there to be less CO2 dissolved. Or if some of this carbon is actually looking at the deep ocean hasn't seen the atmosphere for a very long time. Okay, so it might not be in equilibrium with 400 parts per million. It might be in equilibrium with a pre-industrial value of 280. Okay, so never, you expect to get close to the right answer, but you have to think about why your answer might not be exactly right. There are assumptions that we made in each step of the calculation where we're either over or underestimating. Okay, it's always a good idea to keep track of whether you're over or underestimating, so to make sure that you understand what the processes are. Okay, so I think I've already kind of explained this kind of in some detail. Effectively, only this dissolved CO2 is the stuff that can interact with the atmosphere. So if we are looking at kind of the present situation where we basically partitioned the amount of carbon to the ocean into this carbonate, bicarbonate, and CO2, and that is the CO2 that can interact with the atmosphere. So if we just keep the amount of the amount of carbon in the ocean fixed, but just change the relative proportions of the others. So if we acidify the ocean a bit, we might get more CO2 in aqueous form than we have maybe carbonate ion. And if that happens, then this ratio of the size of this box to this box should stay constant if the temperature is constant. Okay? So that means that if we double the size of that box, we should double the size of the top box. So the speciation of carbon between these three species is really important for determining what the atmospheric concentration of carbon dioxide is. Okay? So ultimately, we've been adding CO2 to the atmosphere and how that's warming the planet and all that kind of stuff. But actually, the atmospheric concentration of carbon dioxide is really determined by what's in the ocean. Because the ocean is really big, it's got a lot of carbon dioxide in it, okay, a lot more carbon in it, and basically the speciation of the carbon into these different forms determines how much is available to exchange with the atmosphere. Okay, so it's really the ocean that is driving the atmospheric concentration. So it's not like, so our emissions into the atmosphere do matter, but a good way of thinking about it is not that we're adding CO2 to the atmosphere, is that we're actually adding it to the ocean. And then the ocean is deciding kind of what pH it is, and then that is determining what's in the atmosphere. Okay? Okay, so to summarize this little section here, the temperature and the partial pressure, so how much CO2 is in the atmosphere, determines how much goes into the ocean. the main form of carbon in the ocean is not CO2, it's actually these other inorganic forms, carbonate and bicarbonate. The pH is really important in determining which of these carbon species dominates and ultimately what the concentration of CO2 aqueous is, which then determines what can exchange with the atmosphere. And the pH is controlled by this, in turn, it's actually controlled by the carbon system as well. And we'll see some more examples of that in a bit. Okay, so if we now think about going into the deep ocean. Okay, so we've basically discussed the exchange with the atmosphere. The deep ocean, so these are measurements of the total dissolved inorganic carbon. So these are the CO2 plus carbonate plus bicarbonate. And you can see actually, so the scale on the bottom doesn't go to 0, it goes to from 1950 to 2,350 micromoles per kilo. So actually, there's actually not a big difference in concentration between the surface and the deep ocean, but there is a difference, so that the deep ocean is enriched in carbon compared to the surface ocean. So this is basically these fluxes between the surface and the deep has basically got a little bit more carbon in terms of concentration. It's got lots more because the deep ocean is obviously very deep, very big. But there is a net flux down into the deep ocean. We need to understand that. And this is kind of problematic, not so much problematic, but we basically need to explain how carbon can get across this boundary between this surface layer of water, okay, which is buoyant, floats around, it's less dense. That sits on top of the deep ocean, which is more dense. Okay, so we have this kind of buoyant surface layer, and then it's quite hard to mix across that, okay, because it's, so water doesn't like to be, well, if you want to move something from down here, it's got a low density. If you want to move it from the top, it's got a high density, sorry, a low density at the top, high density at the bottom. And if you want to move something that's dense above something that's not dense, you need to do work to do that. I mean, having them the other way up is kind of abhorrent to nature. It doesn't like to have the heavy things at the bottom. It's a very stratified system, so mixing between the two is very difficult. But there are some places where that mixing is quite efficient. So in the high latitudes around kind of Greenland, and in this place around Antarctica called the Weddell Sea, there's also maybe some sinking in the Ross Sea on the other side of Antarctica. So in these places, we can have exchange between the surface and the deep water, because at these places the water can get very, very, very cold, okay, because it's cold around the poles, and it can also get quite salty. And the mechanisms for that are not so important for this, but what that does mean, you can make the surface water dense, and that allows it to sink and mix with the deep water below. Okay? And this is important because these regions are very cold, which means that the water can basically take lots of CO2 from the atmosphere, and then when the water sinks, it basically circulates throughout the ocean. So this is a section from the north to the south. Okay, and you can see water sinking down, basically in terms of down into the basically the deep ocean along this way. Okay, so the colour on the background is the carbon content. So you can see the surface ocean has got relatively low concentrations of carbon. Okay, and that low concentration water is basically mixed down into the deep ocean. Okay, in the southern ocean, it's a little bit more different, but you can see water being mixed down. In this case, it's got a lot higher concentration of carbon. Okay, and that's because the surface ocean in the southern ocean actually doesn't mix completely with the atmosphere because of the sea ice and other effects. Okay, so this explains this downward flux. Okay, so we're taking carbon from the surface ocean, moving it into the deep ocean by this basically convection in the polar latitudes. That water doesn't just stay down there, it kind of moves around the deep ocean. So this is a massively oversimplified view of how the water moves around the deep ocean. So it kind of sinks down places like the North Atlantic to the bottom. It flows along the bottom of the ocean. There's also a source here that sinks down. And then all around the ocean, it gradually upwells to the surface. Okay. And we can see the places where this happens particularly strongly. So for reasons of physics, it happens along the equator quite a lot. It also happens in places near coasts where you have strong winds. Blowing along the coasts actually causes upwelling to happen. And this brings that water that's rich in carbon because it's been down in the deep ocean for a long time. And we'll come on to why the deep ocean would actually have be enriched over time. That brings it up to the surface. Okay, so it brings it up to the surface. It warms up. and then releases its carbon to the atmosphere. So those are that kind of flux back up there. Okay? So you can see how that's actually a bigger flux up than there is flux down. Okay, so that doesn't make sense because we already know that the deep ocean has got more carbon in the surface ocean, and if the flux up is bigger than the flux down, that suggests that it should be less. So there must be another flux that's kind of down into the deep ocean, and I guess it's already marked on the diagram here. That's this flux from marine biology. There's a box that says that. So this is what happens with the biology. So we've got the surface layer of the ocean at the top, the deep ocean at the bottom of this kind of like cartoon. And in the surface layer, biology can happen. So phytoplankton, like these kind of diatoms up here, they can take carbon out of the water, basically use the CO2 dissolved in the water to do photosynthesis, and that will make organic carbon. That organic carbon gets eaten by larger organisms like this kind of krill type thing here. And these produce packets of biological material which fall out of the back of the organism, and then those sink down into the deep ocean. Okay, so this can also be eaten by a bigger thing, which produces a larger packet of poop, and that basically causes this flux of sinking organic matter. Okay, so particulate organic matter. That material, as it sinks, it gradually kind of breaks apart, and bacteria kind of start eating that material, and they respire it back out. So they basically take that organic matter, any oxygen dissolved in the water, and they use that to basically produce CO2. So we've got organic matter being produced in the surface ocean. It sinks down, okay? Some of it just dissolves to form dissolved organic carbon, and then all of this organic material that's sinking down into the ocean, that gets respired by bacteria that are present in the ocean, and that releases the CO2 back into the water. Okay, so this is the marine snow kind of sinking down. So that CO2 produced, okay, that can't escape into the atmosphere now because it's in the deep ocean. It's physically separated from the surface. But it will still react with the water to form carbonic acid, which will then break apart and form, in this case, the bicarbonate ion and hydrogen, may break apart some more to form another hydrogen and the carbonate ion. So basically this respiration of organic matter as it sinks down to the ocean is adding hydrogen ions to the deep ocean. It's also adding carbon to the deep ocean. So the total amount of carbon is going up and the pH is going down. Okay? Which hopefully is shown on this diagram here. Yay! So you can see in two different oceans, the Atlantic Ocean and the Pacific Ocean, the surface ocean has got a relatively low concentration of carbon, but the deep ocean is got a higher concentration because organic matter is being added to it and then respired. And you can see the effect on pH here. So the pH in the surface ocean is being reduced as it goes into the deep ocean, as we go into the deep ocean, because of this release of CO2 from the decay of organic matter. Okay? So one of the reasons, if we just flip back, that these oceans are different, okay, if you look at the Pacific Ocean, Atlantic Ocean, so the Pacific has got more carbon dissolved in it than the Atlantic Ocean, and it's got a lower pH. So if we look at where these are on this kind of so-called, sometimes called the conveyor of deep ocean circulation, the water in the Atlantic has only gone from here to the Atlantic, okay? Whereas the water in the deep Pacific has gone a lot further. Okay, so it's been down in the deep ocean for longer, so there's had more chance for organic matter to fall into it and decay. So it's effectively older. So the longer water is isolated from the surface, the higher its concentration of carbon and the lower its pH. Okay? So the longer we can, basically, if we could slow down ocean circulation, if we could make it really sluggish and slow, the water would stay in the deep ocean for a long time and it would accumulate more carbon, okay? Which would mean that there would be less carbon to go into the atmosphere. So one of the controls on how much carbon there is in the ocean compared to the atmosphere is the sluggishness of this circulation and the amount of biological activity happening in the surface ocean. So if you have lots of biological activity, that produces lots of packets of biological material or fish poop. that sinks down into the deep ocean, and if the ocean circulates around very slowly, it means you can build up large concentrations of CO2 in the deep ocean. Okay, so that's what that says. I should have probably said it when it was up there, but there you go. Okay. So just to point out that the amount of carbon you're adding to the deep ocean doesn't really depend on how fast it's dissolved and respired in the deep ocean, because that process is actually almost kind of entirely efficient. Only a very tiny fraction of the carbon actually makes it to the deep sea sediments. So it's mostly controlled by these processes of ocean circulation and the basically effectiveness of this so-called, sometimes called the biological pump. So this is basically biology is taking carbon out of the surface ocean and pumping it down into the deep ocean. Okay, and there's a video that someone's done that I've posted on the Learn site, which you can have a look at for that, which will be kind of useful. Okay, so it's not all kind of one-way traffic. If we acidify the ocean, okay, because the ocean is sitting in a basin made of rock, okay, and particularly made of calcium carbonate, if we try and change the pH, okay, there's a buffering system which basically acts to stop the pH changing. Okay, so the pH will change, but it'll only change by a small amount. Okay, so if we go back to our basically chemical reactions, we add CO2, okay, and then that basically reacts to form carbonic acid, releases these hydrogen ions. Okay, but there is a thing that's stopping that happening. Okay, so we can see the effect of this. So this is CO2 rising through time, which might look familiar from your practicals. And then ocean pH is coming down. Okay, and when ocean pH comes down, it makes it harder for these little beasties here that grow shells, so bivalves, foraminifera, coccoliths. And it makes them harder to grow their shells. So that's effectively, so if we stop this thing happening, so not growing carbonate shells is effectively the same as dissolving them. Okay, so these things are being formed and dissolved kind of constantly in the ocean, and if you reduce the rate of formation, that's effectively the same as increasing the rate of removal. Okay, so if we're basically having this effect of reduced formation of calcium carbonate or increased dissolution of calcium carbonate, what effect will that have? Well, here's the reaction. Here's the important reaction here in the middle. If we take calcium carbonate and dissolve it, it produces calcium ions and bicarbonate ion. This process removes acid from the ocean. Okay? So this means that the pH change in the ocean, okay, is actually buffered by the dissolution of calcium carbonate. So this happens in the deep ocean where dissolution is easier because of high pressure, but can also happen in the shallow water systems. If we make the oceans so acidic that it stops carbonate production in the surface ocean, that might mean that we may, for instance, stop growing the Great Barrier Reef. Okay, so the Great Barrier Reef is made of mostly calcium carbonate. If those corals stop growing, that means that what we're effectively doing is removing calcium carbonate from the system by this mechanism, and that will actually buffer the pH change due to ocean acidification, which will mean that it will increase the capacity or decrease less the capacity of the ocean to store carbon. Okay? So there's this term alkalinity, which is basically the amount of buffering capacity that's added to the ocean by adding dissolved rock into the ocean, or dissolved calcium carbonate in this case. So the more of this stuff that's in the ocean, this carbonate and bicarbonate, through weathering of rocks, through dissolution of calcium carbonate, the more the ocean is buffered against pH change. So this is kind of the one saving grace that has stopped the climate kind of running away into this kind of greenhouse kind of disaster. If this buffering reaction hadn't occurred, or didn't occur, then the ocean would not really be able to uptake the carbon out of the atmosphere. Okay? It would take some up, but it would then acidify and then reduce its carrying capacity. It's this buffering capacity which maintains the ocean's ability to take up CO2, which is really important. Okay, so this is this effect. So if we increase carbon dioxide, we force ourselves this way on the graph. We increase the proportion of CO2 that's dissolved. Increase the atmospheric concentration again. But if actually we start dissolving calcium carbonate, that draws us back over to this side, the safe side of the diagram, which I've ironically put red for safety. Okay, so just to wrap up, so there is a flux out to sediments. Okay, so this is important on the long geological kind of timescales, but on the kind of like the human timescales of anthropogenic CO2 warming, these fluxes from kind of like weathering fluxes from rivers and into sediments are not so important. If we're looking at long geological timescales, then they are, but we're not. So to conclude the marine carbon cycle, so biology and ocean circulation, really important in determining how much carbon is taken out of the surface ocean and put into the deep ocean, because only the surface ocean can interact with the atmosphere. And then the carbonate system, so the buffering by adding or basically dissolving calcium carbonate into the ocean is really important in controlling the pH, because it's the pH that controls which kind of species of carbon, CO2, bicarbonate to carbonate, are important or are the dominant ones. If we allow the pH to go really, really low, then it means that all of the carbon in the ocean will be in the CO2 form, which will mean that we can't put as much carbon in the ocean. Whereas if we raise the pH, if we dissolve loads of calcium carbonate, okay, that actually increases the ocean's ability to store carbon. So it's kind of a little bit, it's completely counterintuitive. If you take limestone, okay, which is made of carbon, and you dissolve it in the ocean, you think, well, that should add carbon dioxide to the atmosphere. But it doesn't. Okay? It raises the pH of the ocean, which means you can store more carbon in the ocean, which lowers the concentration of carbon dioxide in the atmosphere. Okay, so I'm going to stop there, and I just want to show you a better example of this experiment. So this is a video of so cabbage juice. If you get red cabbage and you just juice it up, it's actually a pH indicator, just like the methyl orange, but it's less toxic, although it's cabbage juice. So this is an experiment that there's me, and so if you take cabbage juice and concentrate it in a freeze dryer, that doesn't stop it smelling awful. Okay, it really, really hums. So what we're doing here is putting some of the cabbage juice, red cabbage juice, obviously the other kind of cabbage juice doesn't work, in some beakers of water. And then Rabana, you guys have met Rabana in the chemistry? Yeah? So she had some samples delivered from Antarctica, and they needed to be frozen. So as they were being shipped, they were packed in dry ice. So we had a bunch of dry, yeah, it's quite hard to put that anyway. We had some dry ice we had to get rid of. So we just, so you can see that's the colour of the indicator with normal conditions, shaky camera going on. Just move forward a little bit. Oh, okay, so you can see, oh. Okay, so here's me, safe with like my safety hands, putting lumps of dry ice, so that's just pure CO2, and you see as it's bubbling away, it's releasing bubbles of CO2, and that CO2 is dissolving in the water. And hopefully you can see, maybe you can see that it's changing colour if I make it kind of stealthy. No. Ooh, okay, so you can see now that this has gone pink, and this is still purple. So this is the acidification of the water by adding CO2. You can also do this experiment just by blowing bubbles in kind of cabbage juice, if you're into that kind of thing, which we do for outreach for little kids and stuff. And yeah. So anyway, so that's the kind of fun stuff you have when you've got some dry ice and some cabbage juice. So that's now linked off the Learn page if you want to go and find that video. Okay, and you can also make Halloween jungle juice. Which anyway, let's not do that.